Hi, welcome to another edition of Astronomy for Everyone. My name's Dr. Timothy Day. I have the honor of sitting in for Don Glazier, our usual host, and today we're going to be talking about how elements are made. To help us with that discussion, we are privileged to have Mr. Timothy Campbell. Tim is the president of the Ford Amateur Astronomy Club, and welcome to the show, Tim.
Thank you, Tim, for having me on.
So tell us a little bit about elements. Where do they come from? How did they start? Where do we find them?
Sure. All right. So on your screen, let's just show you quickly an image of the periodic table of the elements. All of these little colored dots represent a different element on the table. These are all the elements that are known to exist. Every one of them is here. Also, the other interesting thing about this table is each element actually has a number.
I remember that from high school, yeah.
And so up in the upper left-hand corner, the first element's number 1. That isn't just an arbitrary number. What it means is that there's actually one proton in the center of the atom, and there's also one electron orbiting out in the shell of the atom. And then over on the other side, the next one is 2, and it has 2 protons and 2 electrons, and so on and so forth, all the way through the table. So, but how did they get here, right? So it turns out at the start of the universe, we didn't have any of these. If I simplify this table just a little bit to just give you an idea of what it is that the astronomers actually see, you can see
they're going away.
We're going away. We're taking away all of them, right? Well, we're not taking away all of them, but we are taking away most of them. All right? And we're left with 11 elements on the periodic table.
Well, that's a lot simpler one. I wish I had that one in high school.
It gets even simpler. So this is what astronomers see when they observe the universe. We know there are more elements out there, but these are the elements that exist in a high enough abundance that they do show up easily through the instruments that we use to measure. The other ones are just too minuscule to detect in large quantities.
Okay.
Of these elements, 90% of all normal matter in the universe, hydrogen.
Really? The simplest one is the one that's the most common.
And you find it everywhere.
No
It's
kidding.
all over the place. Helium, about 10%. And then of the other 9 remaining elements, all of them combined, less than 1%.
So they're just smidgens of all the rest of them. It's mostly hydrogen, a tiny bit of helium, and then just a tiniest salt of just a little bit of all the rest.
That's correct, yep. If we keep moving this along, okay. Once we had the Big Bang, initially nothing but energy comes out. We didn't have any elements at all. It was too hot. There are temperatures that are so high that you can't get the fundamental particles to stick together to form elements. They had to cool a little bit before these fundamental particles.
An unbelievably hot furnace to start. So hot that you couldn't even have atoms.
Yes, exactly. But as this started to cool, a few elements were created. And so these elements are hydrogen,
right,
first of all. We got some helium,
okay,
a bit of that. And then if a tiny amount of lithium, and physicists argue about how much of that we may have got.
So just a trace of that, if any at all.
Right. And the problem is the universe was cooling so rapidly that it couldn't form anything else. My funny comment that I love to point out here is that chemistry class really would be a breeze.
Boy, if it was just hydrogen and helium, I think I could pass that test on the first try.
Sure. So, now let's talk about what a star like the sun does. And before I get into that, let's talk about how 2 elements or 2 atoms come together, or 4 atoms come together actually in the heart of a star to create another element. So I use these tennis balls here as an analogy. I've got 2 ordinary tennis balls. Tennis balls, everybody's had a tennis ball before.
Sure.
It has sort of a rubbery shell to it. We don't really care about the furry coating, but it has a rubbery shell to it. If I take 2 tennis balls and I roll them together at relatively slow speed, they bounce off.
They bounce
off each other. So here's a question for you, Tim. What if I doubled the speed and rolled them together?
They'd bounce off even harder.
Even harder, absolutely. Could I scale this as fast as I wanted to go?
Boy, maybe if you had two cannons and they fired a tennis ball at the same time right at each other.
And so that is the thing. There is a limit to the strength of that shell. There is a point where the shell finally breaks, and you've nailed it, right? So this is exactly what happens in the middle of a star. These atoms are getting squeezed by the tremendous gravitational pressure, and as they are squeezed, they get hotter and hotter, they shake faster and faster, and as they do this, they slam into each other, and when it is hot enough, about 15 million Celsius, they slam into each other so hard that they actually fuse,
wow,
and hydrogen forms helium. It actually takes 4 of these atoms to do this, not 2.
So they really don't want to stick, but if it's hot enough, they have no choice.
Right, they have no choice. They crush in and they become that. It's called the proton-proton chain. We're not going to go through that, but that's what it's called. So our sun made hydrogen is being turned into helium.
Right.
Right. After it's done with that, it will then shift. The star will start to collapse because it ran out of fuel in hydrogen.
Okay.
But as it starts to collapse, it will drive up the temperature a second time. When it does that, helium will then be able to form into carbon and oxygen, and we get that out of our star. Now, for a star our size, that's it. It doesn't have the ability to make anything heavier on the periodic table.
So we get helium and carbon and oxygen and not much more from a star our size.
Correct. At the end of that, the star literally collapses down. It becomes a white dwarf. It's hot, but it's not really producing anything. It's just cooling off. It will take a long time.
So you get the small white cinder that's just cooling off as the universe ages.
Exactly. And an outer shell of gases sort of starts drifting away in space, and this becomes something called a planetary nebula. All right? But if we have a bigger star, so we'll take a much larger star, something like Betelgeuse, about 16 solar masses.
That's an Orion, isn't it?
It is an Orion.
Big red one?
About 16 solar masses, and it will it will go through hydrogen, helium, carbon, oxygen. It will keep going heavier and heavier. It'll go all the way down the periodic table until it gets to iron. When it gets to iron, it's done. No star can fuse anything heavier than iron in the prime of its life. So when it runs out of that, the entire star collapses and explodes in an absolutely spectacular explosion called a supernova.
Wow.
It's huge, creates an enormous amount of light, outshines the galaxy that it's living in.
The entire galaxy,
Yes.
one star.
One star. A tremendous amount of energy is released, and all of the rest of the elements in the periodic table can be fused in the heart of that star, many of them for mere seconds. Right? So elements like gold, maybe 15 seconds. That it's got enough energy to fuse gold.
So if I have a gold wedding band, you're telling me that the gold was actually made in the heart of a supernova in just a blink of an instant.
It is, in fact, the only way to make it. And so what happens is you get one of these supernovas about once every 100 years in a galaxy our size. They don't come up very regularly, but as they do come up, in the age of our universe, in the age of our galaxy, probably about 130 million supernovas would have occurred in just our galaxy alone.
Wow.
So that's quite a bit. All right. So as these things are happening, I'm animating a slide for you here, and you can see elements dropping in. These are major elements necessary to support human life. As I drop these in,
Carbon and oxygen, hydrogen, nitrogen, all the things that we need to be alive.
you can see things like calcium.
Calcium,
Got to have some of that.
magnesium, strontium.
You'll find there are also some trace elements that come in, and some of these come from the part of the periodic table that can only be made in a supernova. You see, for example, iron. Now, we call it a trace element, but it's in your blood, and if you didn't have it...
It's hemoglobin. If it's not there, you're not
there. That's right.
All right.
So you absolutely have to have this stuff. When that happens, that star creates something called a supernova remnant. Here's an image of the Crab Nebula. It's a remnant about 1,000 years old. In the heart of it, however, there is something called a neutron star.
Oh, that's very cool. So there's a little star in the center those waves are coming out, and all that gas came from that explosion.
And they call that a pulsar, and it just sits there ticking and pulsing.
So that's an amazing way to end this segment. If I understand correctly, literally every atom that we're made of, my body, your body, the chair, the computers, it's all from atoms that were created at the center of a star or maybe even a supermassive star. And it's an incredible explosion that gave birth to everything else that the universe is made of.
Absolutely. We literally are made out of star stuff.
That's an incredible understanding. For more information about the show, please go to the website address at the bottom of the screen. And at this point, we're going to throw it to Steve for Term of the Month.
Thanks, Tim. The term of the month for July 2016 is Fraunhofer lines. Fraunhofer lines are a set of spectral lines observed as dark features in the spectrum of the Sun. English chemist William Hyde Wollaston noted the appearance of a number of dark features in the solar spectrum in 1802. Joseph von Fraunhofer rediscovered these lines in 1814 and then measured the wavelengths of some 570 of these lines. We now know about thousands of these lines. 45 years later, Kirchhoff and Bunsen noticed that several spectra of heated elements matched Fraunhofer lines. On the Sun, the absorption happens in the photosphere, where cooler gases absorb the spectra that was emitted in lower, hotter gases on the Sun. Also, oxygen in Earth's atmosphere was also detected. So in this graph, you can kind of see where some of these things are absorbed in the spectrum. And that is the term of the month for July 2016, Fraunhofer lines.
Welcome back to Astronomy for Everyone. I'm Dr. Timothy Day, and we continue with Mr. Tim Campbell, president of the Ford Amateur Astronomy Club, and someone who knows an awful lot about light as both a professional and an avid amateur photographer. In this part, we're going to talk about how is it that we know certain elements are in stars that are tremendously far away from us. How can we possibly tell?
So that's a great question, Tim. Years ago, astronomers believed that they could never possibly know what a star was made out of unless they could visit that star and scoop a piece of it up.
One would think.
So many years ago, someone discovered that there are secrets hidden in the light that will tell us what the star is made out of. So in the first part of the program, we talked about all of the various elements that astronomers can observe. Now we're going to talk about how it is that we know that those elements are there, and to do that we use spectroscopy. So just a little intro to explain spectroscopy. Normally, most people are probably familiar with this idea that if you take a prism, piece of glass,
right,
sort of triangular shape, right, and you shine a white light through it, it creates a rainbow.
I remember doing that in the classroom when I was a kid. Yeah.
Absolutely.
Yeah.
So what I have here is a sheet of film, and instead of one prism, you can imagine about 100 microscopic prisms laid down in every inch of this material. They basically drag a comb over it to make it. And so this is sort of a prismatic film paper. We call it diffraction grating film. And when we hold this in front of a light, you'll see what happens to the light. And so to start this, why don't we just start down here?
Sure.
So this is just an ordinary incandescent light bulb that I'm going to turn on. This one happens to be designed for aquariums and display cases, but it has just an ordinary incandescent filament. I like it because the filament is long and straight, and so it happens to show up really well when we do this experiment. And if you look at that, it looks like a whitish light.
Something like my grandmother used to have at her house.
Exactly.
Just a straight up and down white light bulb.
Exactly. So, but watch what happens when we hold this diffraction film in front of it.
I can see a rainbow.
You see a whole rainbow. This is what we call black body radiation. It's a continuous spectrum of light source. It's not actually created by gases glowing. We're actually heating a piece of tungsten to make this occur, and that's what we get. So this is just the effect of putting this film in front of the light.
So all those little prisms in there are what's giving us the red, the yellow, the green, the blue that I see when you hold it up in front of that light.
And all of those colors are actually in that light. This just smears them out so that we can identify all of them.
So they're there. I just see them as white unless there's a prism.
Sure. That's it. All right, so now next up we have the simplest element on the periodic table. This is hydrogen if you've ever seen a neon sign on maybe a store or something like that. It's a glass tube. It's full of a gas.
Right, right.
This is also a glass tube, and it's full of a gas, but this gas happens to be pure hydrogen.
So there's all just hydrogen gas inside that glass tube, nothing else.
Just hydrogen. So we're going to switch this on. It's going to excite the gas, and it's going to start to give off a light. And you can see that light there. And what color would you say that is?
Well, it kind of looks like a magenta color almost in the center to me. Sort of got a reddish tint to it.
All right, so now let's hold this film in front of it and watch what happens.
Wow. So now I'm seeing lots of other colors as well.
And dominantly, there's a very strong red color that we see. There's also a little bit of a little aqua green blue
it's like
color.
A teal color, yeah.
And then there's also more of a middle blue, and then there's a really, really deep blue, nearly purple almost at the end of it. There are actually one more color even beyond the visible spectrum that we can't see with our eyes that exists. But it's fairly simple. About 5 bands of color that we get out of that particular light.
So those bands of color were hiding inside of that original magenta I saw, and you made them you teased them out so we could see them by using the diffraction grating.
Absolutely, and here's the important bit. These are hydrogen atoms. Every hydrogen atom in the universe behaves precisely the same way. And so what we're getting is what looks like sort of a rainbow-colored barcode teased out of the light, and that's what hydrogen looks like. Every hydrogen light will do the very same thing.
So you're telling me that the hydrogen light we just looked at right here in front of us is the same kind of hydrogen light we would see a billion light years away?
Exactly the same. Now what will happen, however, is if that light source is moving away from us rapidly, in the same way you hear the pitch of sound seem to go higher or lower as a train passes by, light does the same thing. And so the spacing between the bars on that colorful barcode will stay exactly the same, but it might shift a little toward the red side, or if the star or galaxy or whatever we're looking at is moving away, if it were coming at us, it would shift toward the blue side.
So the spaces between the lines stay the same, but the whole set of lines goes one direction or the other.
Yes.
Is that a good understanding?
Yes, that's exactly right. And so we call that red shifted or blue shifted.
I understand.
All right. So if we go to the next light source and we turn this on, we get a different color light. This one, what color would you say that is?
That's a much lighter pinkish sort of a color, at least as far as my eye can make out.
So I think that this is maybe a little on the peach colored side.
I'll give you peach.
A tiny bit.
Yeah,
So
sure.
so it looks like one color.
Okay.
And now let's just hold up this film in front of it and see what happens.
Wow. Big difference. I see yellow. I see another aqua line. I see a little purple. I see a red line, maybe a green.
So there's a very strong, dominant amount of yellow, which is what gives it sort of that peach color. And then the other colors are a little weaker, but they all add to it. And when you add them all up, you get that color. And so that one happens to be helium. So we mentioned earlier that the hydrogen gets fused in the stars and makes the helium. And so this gas gets turned into this gas in the heart of a star.
Right.
And this is how we know that it's present.
So we hold the diffraction grating up in front of that light and we say, I know that pattern. That's the pattern that we see when we look at a helium lamp or a helium light. And so now if I see a star very, very far away that's showing me that, I might go, hey, I bet you there's some helium in that star.
Absolutely. Yep. So, and then we have one more to show off. This one happens to be argon gas. We like to use this because it's particularly colorful. You'll see why in a moment. So go ahead and judge that color. What do you suppose that is?
Again, that's a little closer to the hydrogen, but sort of a pink with a little bit of a purplish cast to it as well.
It's maybe a little paler than the
I would
pink
agree.
that we got out of that one.
Yep, that's a little bit paler.
So now when we hold the light up in front of this one,
what do we get? Wow, that's busy.
A lot.
There's a lot going on there.
There's a lot going on.
A big red line. I can definitely see green. There's some purple involved on one side. A little bit of yellow between the red and the green. There's a lot happening there.
Absolutely. So each one of these atoms represent heavier elements on the periodic table. There are more electrons in the shell of the atom, or protons in the heart of the atom. So as you mentioned earlier when we were off camera, it's a more complicated atom.
So this is a very simple atom, the hydrogen. It's about as simple as we get, right?
It is
one proton, one electron.
Yep.
And now we got 2 protons and 2 electrons, a little
Yep.
busier. And now we're over to argon, and there's multiple protons and multiple electrons.
Absolutely.
And so we get a lot of different colors.
Yep.
That's pretty interesting.
All right, so when we look at stars in the sun, for example, like stars like the sun, I should say, you can read these barcode patterns with all of these colors overlaid on top of each other, and you can figure out that this, imagine if I could combine this gas and this gas inside the same tube at the same time, you would actually see both signatures inside that tube. So you can kind of add them all up and figure out what all of the, this is just one element at a time that we're doing, but a star would actually have lots and lots of elements.
So you can see elements overlapping on top of each other with a diffraction grating if there's more than one element present.
Correct.
Okay,
Yep.
all right.
That works for us. So this is sort of the fun hands-on participation part of the experiment. But let's talk about the science behind why this actually happens. So on the screen, I've got an image of essentially an exploded image of what would be inside an atom if we could sort of slice the atom in two and look inside it. There's a little tiny red dot in the middle of the image that would represent the nucleus of the atom. And then there are a series of these rings going around it, and each one of these rings represents what you can think of as a shell.
Okay. In our final minute, could you give us some idea about what it is that takes place with the different shells?
Sure. So let's just pick on just the hydrogen because that's the easiest one. So you can see I've got 6 different shells here. You can think of these like lanes, except they are shells.
All right.
And normally the electron would be racing around on track number 2. If that electron gets hit with a photon, some light, that happens to match the frequency it wants, it has the right energy level to jump from track 2 to track 3, it will jump to a higher level shell. And in so doing, it will steal that photon of light. In other words, it subtracts the light from
It literally sucks it in, takes it away.
And so the energy doesn't go away. The energy was flying through space. Now the energy is trapped in that hydrogen atom.
And then what happens?
So if then later that atom gives off energy, it will release that atom. It will drop from shell number 3 back down to shell number 2 again and release that photon of light at precisely the same wavelength as though it were never absorbed.
So that's the way we can tell that there are certain elements present in stars no matter how far away. We see the characteristic light, the photon that comes from each different element, and we say, aha, even though that's really far away, that element must be present.
Absolutely.
And that's an incredible trick.
And right, so I just showed one track only, but there are actually many more. So for the hydrogen, there's actually about 4 of them that we tend to care about. And we could do that with each element.
Wonderful. Thank you so much for your time today. If you have any questions, please don't hesitate to go to the Astronomy for Everybody email site. It's at the bottom of your screen right now. And we love to hear from you. We would love to have suggestions for more shows or questions about this one. And with that, I'm going to throw it to Steve Whitty for What's Up in July.
What's up in the night sky for July 2016? We just had the summer solstice. That was the longest day of the year, so days are getting shorter. The sun rises at 6 at the beginning of the month and rises at 6:25, so we lose 25 minutes on that side. And then it also sets at 9:13 at the beginning of the month and at 8:53, so like 20 minutes on the other side. The month starts with the new moon on the 4th of July. Then on the first quarter, the first quarter is on the 11th, the full moon is on the 19th, The third quarter is on the 26th. Mercury does something very strange this month. We have superior conjunction on like the 7th, so you're not going to be able to see it then, but it rises at 5:30 a.m., so that's before sunrise on the 1st. And at the end of the month, it sets at 9:51 p.m., so that's after sunset. So you should be able to catch Mercury just at the ends of the month. Venus is a total heroic effort. I don't recommend looking at Venus this month. Mars, Jupiter, and Saturn are all together. Here we have it at a nominal 10 p.m. on the 15th, and we get the moon for free. You're going to be able to find Saturn without the moon. I mean, it's pretty bright. You have these planets setting, Mars setting, around 3 a.m., Jupiter setting around midnight, and Saturn setting around 3 in the morning. Now I'd like to talk about astronomy at the beach. September 9th and 10th, Friday and Saturday, at Kensington Metro Park, Maple Beach. Friday and Saturday at 5 p.m., there'll be some solar viewing, some daytime solar viewing, and there'll also be nighttime viewing. Lots of telescopes. There are several presentations. There's Make a Comet with dry ice. There's 3D tours of the solar system and much more. And we have a keynote speaker, Fred Espenak, who's going to talk about the 2017 eclipse of the sun. It's going to go all the way across the United States, and this is an event that, if you can make it, would be an awesome sort of thing to do. So there are preps to do. Fred will tell you what to do. And that's what's up in the night sky for July 2016. Keep looking up. It's the best free show over your head every night.